Whenever you're done with a variable in Python, it just sort of disappears, right? Poof, gone. It feels a little bit like magic. But today we're going to pull back the curtain and see exactly what's going on under the hood with Python's memory management.
Seriously, think about it. As a developer, you've probably created thousands, maybe millions of variables and objects without ever stopping to think, hey, where does this stuff go when I'm done with it? You just trust Python to handle the cleanup. But how does it know? How does it tidy everything up so neatly without you even asking?
Well, it's not magic. It's a really clever system. And we're going to break it down. Because understanding how Python handles memory isn't just a fun fact. It's something that will genuinely help you write more efficient, less buggy code. This is the stuff that matters when performance is on the line.
Okay, so let's start with the absolute core of it all. It's a simple but really powerful concept called reference counting. This one idea basically governs the entire life of every single object you create in Python.
To make this super intuitive, let's use an analogy. Just imagine an object, let's say it's a list, is a coat that you've checked in at a party. Now, every variable that points to that list is like a claim ticket for that specific coat. Make sense, right?
So here's the trick. Python attaches a tiny little counter to every single object it creates. And this counter does one simple job. It keeps track of how many tickets, or variables, are pointing to that object. That number is its reference count.
And the life cycle is actually pretty simple. When you first create an object, its reference count starts at 1. You get 1 ticket. If you create another variable that points to it, the count goes up. Hand out another ticket. And when you delete a variable or point it somewhere else, the count goes down. You turn in a ticket. The moment that count hits 0, that's when Python knows nobody's coming back for that code, and it can free up the memory.
And you can actually peek at this yourself. We can use the sys module to check. Now, if you run this code, you might think the count for x would be 1, but you'll actually see 2. Why? Well, it's a funny little quirk. The getRefCount function itself needs a temporary reference to the object just to check its count, so it bumps it up by 1 for a moment. It's a cool sign that you're looking right at the internal machinery.
All right, so reference counting is the first big piece of the puzzle. The second piece is realizing that not all Python objects are the same. They fall into two really important categories, mutable and immutable.
So on one side, you have mutable objects. Think lists, dictionaries, sets. These are things you can change after you've created them. You can add items, remove things, whatever. On the other side, you have immutable objects. These are your numbers, strings, and tuples. Once you make one, it's set in stone. Its value cannot be changed.
And this difference has huge implications. Watch this. We make a list called x. Then we say y equals x. Now, both variables are pointing to the exact same list. So because lists are mutable, when we change the list using x, well, that change shows up when we look at y. They're both just tickets for the same coat. And by the way, this is a super common source of bugs. Passing a list into a function and not realizing the function is changing your original list.
Now, let's flip that and look at a mutable integer. We set x to 5 and we make y point to it. But when we say x equals 6, we aren't changing the number 5. You can't change the number 5. Instead, Python just creates a brand new integer object, the number 6, and points x to that new object. Meanwhile, y is left completely untouched, still pointing to the original 5. See the difference? This whole idea leads us directly into another classic Python topic and a common point of confusion, the difference between identity and equality. Let's call it the is versus double equal showdown.
It's actually pretty simple when you break it down. The double equals operator double equals checks for equality. It asks, do these two things have the same value? But the is operator, it checks for identity. It asks a much stricter question. Are these two variables pointing to the very same object in memory?
And here is the perfect example. We create two lists, A and B. They have the exact same contents. So if we ask A equals B, the answer is true. Their values are equal. But we created two separate lists. They are two different objects in memory. Think of it like two identical coats. They look the same, but they aren't the same coat. So A is B is false.
And we can prove it. You can use the built-in ID function to see the unique memory address for any object. If you print the ID of A and the ID of B, you'll see two completely different numbers. That's the proof that they live in different spots in your computer's memory.
Okay, so now that we've got the fundamentals down, reference counting, mutability, and identity, let's dive into the really fun stuff. Some of the secret optimizations Python is doing behind your back to make everything run faster. So let me throw a puzzle at you. Based on everything we just learned about lists, you'd probably expect this to be false, right? We're creating A, then we're creating B. They should be two separate integer objects. But if you actually run this code, Python tells you it's true. How is that possible?
And get this, to make it even weirder, if you do the exact same thing with a bigger number, say 1,000, all of a sudden you get false, which is what we expected in the first place. What on earth is going on here?
The answer is a really slick optimization called interning. See, to save time and memory, when Python starts up, it pre-creates a whole bunch of common immutable objects, like small integers. So when you ask for one of those numbers, Python doesn't bother making a new one. It just hands you a reference to the one it already has in its cache. And that solves our little mystery. In CPython, the standard version of Python, integers from -5 all the way up to 256 are pre-cached. So 100 is in the cache, and A and B both point to the same object, but 1000 is not, so Python creates two separate objects. Now here's the most important part. You should never write code that relies on this. It's an internal detail. For checking values, you should always use double equals.
Another one of these cool tricks is something called a free list. The best way to think about this is like a private recycling bin for certain objects. When an object's reference count hits 0, instead of giving that memory back to the operating system right away, Python might just toss it onto a free list. Then, the next time you need a new object of that same type, Python can just grab one from its recycling bin. It's way faster than having to ask the OS for brand new memory every time.
All right, we've gone on a pretty deep dive here, from the basic rules of reference counting all the way to these clever optimizations happening behind the scenes. So, let's bring it all back. How does knowing this stuff actually make you a better coder? Let's just do a super quick recap. First, Python's automatic memory management isn't magic. It's all driven by reference counting. Second, remember the showdown, is for identity, equals is for equality. Knowing which one to use is crucial. Third, that distinction between mutable and immutable objects, that's your key to avoiding some really confusing bugs. And finally, all those little optimizations like interning are working hard in the background to make your code efficient.
So now that you've seen the machinery behind the curtain, the real question is for you. Thinking about your own projects, where can you use this new understanding of Python's memory model to make your code even better?